In the mid-1950s, the United States officially transitioned its live television broadcasts from black and white to color. With the press of a heavy studio button, vibrant hues instantly flooded living rooms across the country. But that seamless launch was a complete illusion. Engineers had actually figured out how to record and broadcast color images nearly 3 decades earlier. If the technology already existed in the late 1920s, why were millions of viewers stuck watching grayscale static well into the atomic age? Capturing color was not a simple matter of swapping out a camera lens. It required an escalating engineering war against 3 distinct bottlenecks, forcing inventors to outsmart physics, severe hardware constraints, and finally, strict government regulations. The very first hurdle was strictly physical. In 1925, Scottish inventor John Logie Baird built the first functional television. He used a photoelectric cell, a special component made of thallium that measures light intensity and converts it directly into an electrical signal. To feed light into that cell, Baird relied on a massive wooden disc. The wheel had 30 holes arranged in a spiral pattern. As it spun rapidly in front of the subject, each hole scanned a tiny vertical strip of the image, slicing the light into a continuous electrical feed. By 1928, Baird managed to add color. This schematic shows how he grouped the spiral holes into 3 distinct sections and covered them with physical red, green, and blue filters. The disc scanned the frame one color at a time, recording light values sequentially. The resulting image was vibrant, but it was also incredibly tiny and ran at a choppy 5 frames per second. To achieve a sharp resolution and a smooth frame rate, you would need a dramatically larger disc. Spinning a wheel of that size fast enough to meet modern visual standards would generate lethal mechanical forces, tearing the machine apart. Television couldn't rely on moving physical parts. It had to move at the speed of electrons. This forced a shift to the electronic era, powered by the cathode ray tube. This vacuum tube used magnets to precisely steer a beam of electrons onto a glass screen, completely replacing the heavy wooden disc and perfecting black and white broadcasting. Inventor Vladimir Zworykin matched this display technology with the iconoscope, essentially the world's first true video camera. Instead of a wheel, it used a sheet covered in thousands of tiny photosensitive grains to record light electronically. With the electronic foundation set, engineers at RCA tried to introduce color through sheer brute force. They built massive arrays that bolted 3 separate cameras and 3 distinct display tubes together, splitting the incoming light into red, green, and blue streams. The result was an unmanageable mess. Perfectly aligning 3 separate projections was maddeningly difficult, and multiplying the hardware made the television sets 3 times as expensive. It was completely unviable for a consumer market. RCA eventually found a brilliant hardware solution called the shadow mask. Instead of requiring 3 separate tubes, they placed 3 precise electron guns into a single glass housing, aimed at a screen coated in a triangular pattern of red, green, and blue phosphors. To make it work, they placed a metal plate with thousands of tiny holes directly behind the screen. Because the 3 electron beams approached from slightly different angles, the holes forced them to strike only their corresponding color dot. The triad of dots was so small, the human eye blended them into a perfect color image. Engineers finally had a reliable, affordable color screen. But the moment they solved the hardware problem, they slammed into an invisible regulatory wall. The Federal Communications Commission carefully managed the radio spectrum to protect things like military and aviation frequencies. They dictated that every television channel had to fit perfectly inside a strict 6 MHz bandwidth. Broadcasters also faced a massive consumer trap. There were already 5 million black and white televisions sitting in living rooms across the country, and networks refused to render them obsolete. This created an impossible paradox. Engineers had to somehow transmit 3 times the visual data, the red, green, and blue values, through the exact same narrow bandwidth, all without breaking the signal for the older televisions. This animated wave illustrates the first step of their mathematical hack, the Luma signal. They took the incoming red, green, and blue data and combined it into a single wave that dictated overall brightness. This baseline wave was exactly what standard black and white televisions already expected to see. Next, they isolated the pure color data and separated it into 2 independent signals. The I signal covered the orange and blue hues, while the Q signal handled the greens and purples. To compress all this into the airwaves, they phased the two color signals 90 degrees apart and mathematically combined them. They targeted a specific frequency slot, exactly 3.57 MHz, and tucked this combined color data directly into the gaps of the main Luma wave. The result was an elegant broadcast loop. Black and white sets naturally filtered out that 3.57 MHz frequency and played the Luma brightness perfectly. Meanwhile, color sets identified a short burst of a reference sine wave at the start of each line, allowing them to reverse the formulas and extract the individual red, green, and blue values from the encoded signal. Engineers had created a mathematical illusion, squeezing an immense volume of color data through a narrow broadcast pipeline that was never designed to hold it. This dense encoding standard allowed the color era to seamlessly piggyback on a massive, pre-existing black and white infrastructure, delivering a vibrant picture without abandoning a single viewer. The engineering was so robust that this exact analog standard dominated the airwaves globally for over 60 years, only yielding when digital broadcasting finally took over in the 2000s. The decades spent fighting physics, hardware bulk, and bandwidth limitations to broadcast those first vibrant images represent a masterclass in problem solving. The invention of color television remains a testament to innovation born from necessity, a brilliant technological leap achieved by navigating the unforgiving constraints of the real world.